Okay, so anyway, a similar question that keeps coming up here, and the question is kind of like this: how do I answer these questions with what formula do I use to answer this question, and so on and so forth? The idea is not necessarily to know what formula you're going to use, especially in this chapter. The idea is to understand what is happening with the energy. So when you start a problem, you should look at all the kinds of energy that you have. Let's say that you have the energy, you have a problem where a car goes down a hill and hits a spring or something, or it gets launched from a spring and goes up a hill, whatever. Doesn't really matter. Let's say that a car is starting at the top of the hill, and it has velocity 0. No, let's say it has a velocity of 5 at the 5 meters per second at the top of the hill. And let's say the bottom of the hill is going to be our height equals 0, so this is y equals 0. And let's say that the top of the hill is y equals 10 meters. The car is going 5 meters per second. It has some velocity, and that's a kind of energy. So what we need to do is we need to say we have some kinetic energy at the top of the hill, or initial kinetic energy. Because we're starting with some kinetic energy. We also have some potential energy at the top of the hill. We have some potential energy, which is gravitational potential energy, because it's due to us being higher up in gravity than down here. And those are really the only two types of energy that we have so far. When we get down to the bottom of the hill and we compress the spring, so we hit the spring here and make it all tightened up, so our car is now sitting right here in front of it. And the spring has stopped us, so we got faster as we went down the hill. And the spring has now stopped us. So where has the energy gone? Well, if we're stopped, we don't have any kinetic energy to end with. So no kinetic energy final. And our potential energy is also 0 because we're at y equals 0. Remember, potential energy is equal to mg times h, and our height is 0 at the end. So we don't have any potential energy gravitationally at the end of the problem. But we do have some energy that we put into the spring. When our car hit the spring and squished it, it turned all the energy that we had at the beginning of the problem into potential energy in the spring. So there's a potential energy being stored in the spring, and that's spring potential energy. Now, assuming that there's no work done, assuming there's no friction done in this problem, then this is all the energies involved. And what the work energy theorem says, or what the conservation of mechanical energy theorem says, either way you want to call it, doesn't matter, says that all the stuff that happens at the beginning, all the energy that you have at the beginning, has to equal all the energy you have at the end. So in this case, we have the kinetic energy initial plus the potential energy gravitational at the beginning. These are our two beginning energies, and those have to equal the energy at the end, which is all spring potential energy. Now, what do you do with these things? Well, each one of these has a definition. Kinetic energy is 1/2 times mass times velocity squared. Let's say that we told you the mass and we did tell you the velocity, then you're good. You can calculate that. You can get a number for that. Potential energy is m times g times h, where g is 9.8, positive 9.8. So m, the mass of the car, times the gravitational constant, times how high it is above the 0 point. Spring potential energy, if you go back through it, through your section on spring potential energy, is 1/2 k times x squared. So you would need, if you wanted to know this number, you would need to know how much the spring compressed and the spring constant. Now, I've told you what h is, and so I would have to tell you one more thing for you to calculate something from this equation. I'd have to either tell you the k constant, the spring constant, and you would calculate how far the spring compresses, x, which is x, or I'd tell you how far the spring compresses and you'd have to calculate the spring constant, one or the other. But this is pretty much how you do every problem in this entire chapter. There are different versions of this equation. Some of them are simpler than others. Some of them only involve the kinetic energy. Like the first one, the work energy theorem, it only has kinetic energy in the equation and work in the equation. So work can be in this equation too. If you have friction doing something in here, then the friction is going to, or the work done by friction, the work done by external forces, is either going to be put on this side as a minus the work. You can put it on that side, or you can put it with the final energies by adding the work. Either way you want to do it. But the equation for that is in there too, in the conservation of mechanical energy system. The thing that students tend to forget is that these equations are not complete. They don't tell you, they don't plug everything in for you. For example, the kinetic energy, they don't plug in 1/2 mv squared for the kinetic energy. You have to know that. You have to go ahead and do that. You have to understand that you can solve for the velocity. If you have an equation that has kinetic energy, you can solve for the velocity, because velocity is in kinetic energy, right? If you're looking to solve for how high something goes or how high it fell, you can get that from this equation if you have a potential energy, because that includes height. Right? If you want to know how far a spring gets compressed, you can get that from the spring potential energy. So the overall equation is the overall work conservation, work energy kind of equation kind of thing is you add up all. Well, you could even say this. You could say that the energy initial minus the work done by non-conservative forces like friction and sound and heat and stuff like that equals the energy final. Or you could make it a little more explicit. You could say all of the kinetic energies added together. So if you add up all the kinetic energies initially, sum of all the kinetic energies, plus the sum of all the potential energies. So you add up all the different kinds of initial potential energies that you could have at the beginning. And you might not have any potential energies. You might not have any kinetic energies. That's fine. You might not have any energy to begin with at all. And then your final energy would have to equal 0, right? So if you add up all your initial energies and then subtract off the non-conservative work done by friction. And remember, work is not something that we'll necessarily tell you. We won't necessarily tell you it did this much work. You might have to plug in the force done times the distance that it was done times the cosine of the angle between them. Remember that equation for work. FD cosine theta. You might have to use the definition of work yourself and figure that out. And that's going to equal the sum of all the final kinetic energies plus the sum of all the potential energies, possibilities, final potential And that is pretty much it. That right here is this chapter in a nutshell. Each one of these things has definitions: 1/2 mv squared, 1/2 kx squared for springs, mgh for gravity. Work is force times distance times cosine of the angle between the force and the distance, so on and so forth. So these things each have definitions that you have to plug in as you need them. And some of these may even go to zero, but the big deal in this problem is setting it up, figuring out what energies there are and how to calculate. Now, when it comes to work, remember that this equation is always valid. For work, what is the cosine of 90 degrees? Zero. So if your force is going one way, if you're getting pulled in one direction, but you're going another direction, what is the work being done on you? Work equals force times distance times cosine theta. So the angle between your displacement and your force are 90 degrees. That cosine is going to go to zero. There is no work being done. That is true with moons going around planets, for example. Cars going around turns. The work being done is equal to zero because it's not being done in the direction that the car or the planet or whatever else is moving. Trick question. All right. I answered everybody's email questions and gave you a little bit more specifics, but pretty much this was my answer every time. Some variation on that. Does anybody have anything else they want to? That they want to ask about Chapter 7 before we move on here? Okay, I extended that till tonight so you can finish it up tonight. Today, I've been writing on my board and I haven't been showing you it. Haven't been paying attention to it. Sorry, that probably maybe. Let's go back and show you again. So here's the equation. When that thing warms up. Hoping they're going to replace my projector TV screen soon. So I have to wait for the warm up. So here is the final equation I was talking about. The initial energy minus the non-conservative work equals final energy. Here's your sum of kinetic energies, sum of potential energies minus the non-conservative work equals kinetic energies final plus sum of all the potential energies final. And you can either subtract the work done by friction on this side or the work done by any non-conservative force, or you can add it to the final side. Either way it works out. But in any case, work done by anything is always force times displacement times, force times distance times the cosine of the angle theta between the force and the distance moved during that force. Sorry for that. Okay, I might just get sleepy during class today because I worked really hard this morning lifting chimney blocks up to the top of my house. So I'm exhausted. I've already fallen asleep in my office once this afternoon, maybe twice. But today we're going to talk about momentum. In particular, there are a few different types of momentum. We're going to talk about linear momentum, which is the kind of momentum that things have when they're moving in straight kind of lines. It's actually the least general type of momentum. We'll learn more about momentum in chapter 10, more general thing. We mentioned before that that energy is not technically conserved because Einstein theoretically proved that energy and mass are the same kind of thing, and they can, well, they're not the same kind of thing, but they can be interchanged for each other. In other words, you can turn mass into pure energy, and you can turn pure energy into pure mass. And it's a strange thing, but it's true. And so energy is not technically conserved, and neither is mass. However, momentum, as far as we can tell in all of our studies in the universe, momentum is truly conserved all the time. Feels strange, I don't know why. But anyway, maybe I should just stand up all the time. Too tired. So momentum is conserved all of the time. And what is the difference? Of course, this has come down to many scientific experiments over the years and some definitions and everything else. And the word momentum and the word energy mean different things in the original Latin that they come from, or Greek that they come from. Momentum, I believe, is Latin. I think energy comes from the Greek, but I don't actually remember. Have you guys ever seen a rugby game? That's an exciting sport to watch. Yeah, it's fun. It's totally legal to lift people up in the game so that they can jump. You can throw people in the air to intercept a pass, and you can climb on people's backs. They'll make pyramids of 3 high people climbing up on top of each other to block a pass or to throw a pass inbounds or whatever. It's pretty funny. It's fun sport. Anyway, my alma mater, BYU, is very good at rugby. We have a lot of people from New Zealand and Australia, and Samoa and Tonga at our school, so it's like their national pastime out there in the Pacific Islands. Anyway, so we're going to talk about this momentum thing. It turns out momentum is both a simpler equation than energy was. Remember, kinetic energy was 1/2 mv squared. Potential energy was mgh, or 1/2 kx squared. So fairly complicated. But energy was just a number. Energy was not a vector. It didn't care about direction. It's just an amount of something. Momentum is a vector, like velocity is. In fact, it uses the velocity vector as part of its value. So to calculate the momentum of something, you have to know its velocity. You have to know how fast it's going and which direction it's going in. And then you multiply it by its mass, and this quantity is now a conserved quantity. If you start off with a certain amount of momentum and no external forces come and act on you, then you're going to maintain that momentum. Your momentum later will be the same. Now this is true for a system of masses as well. So if I have 2 objects that have momentums, and I add their momentums together, and then they interact with each other. Say they bounce off of each other, or they push on each other, whatever else. As long as nothing outside came in and messed with that system that we defined, then the momentum will be conserved. And the truth of the matter is that momentum is conserved, generally it's conserved no matter what. Even if you have things coming in from the outside and interacting, momentum is always conserved. It just becomes very difficult to measure and very difficult to track, usually because of very, very large objects that are involved. So for example, right now, you could say, I have 0 momentum because I'm just standing here, not moving on. And then I begin to walk, and you say, well, now you have a momentum. Now your momentum is equal to your mass, which is whatever it is, and it's equal to and multiplied times your velocity, and that gives you your momentum. Well, look, I just changed momentum. I'm going the other way now. I'm moving about the same speed, but I'm going a different direction. So that's a different momentum. My first momentum was about 1 meter per second this way. Now my second momentum was 1 meter per second this way. Completely different momentum, same velocity or same speed, but different direction. Same mass, but different direction. So obviously, my momentum didn't start the same as it finished. I started with zero momentum, and then I went to a momentum that way, and then a momentum this way. So how does that count as conservation of momentum? Well, the thing is that momentum transfers into the earth, and from the earth into me. But when I push on the earth and it pushes back on me, I don't push on the earth very much. It doesn't really move very much. But it does move. It doesn't take much movement for the earth to get the same amount of momentum as I have going that direction. And so the momentum of the earth, as I push the earth this way, it pushes me this way. We get an equal amount of momentum from each other, but in opposite directions. And so those two momentums cancel. You get let's call it 100. We'll call it 100. Let's see, momentum is in kilogram meters per second. So maybe we get 100 kilogram meters per second of momentum this way from me, but the Earth gets 100 kilogram meters per second of momentum in the opposite direction, which is not even a measurable amount of movement for the Earth. The Earth is so huge. Its mass is so large that the amount of velocity it needs to get 100 kilogram meters per second of momentum is extremely tiny. So tiny it's not measurable. However, we have seen enough examples of this throughout, and we've never seen an example where it isn't conserved, where it isn't always just passed around. You give momentum to something else, you take momentum from other things. Momentum is passed around from one thing to the other, but it is never created or destroyed just spontaneously in the universe. It's just passed around. So let's do some examples, some very simple examples of momentums. We have a 100 kilogram football player. So now we're just going to calculate the instantaneous momentum of this football player. He's running at 8 meters per second, 110 kilograms. And then the momentum of a 0.410 kilogram football has a speed of 25 meters per second. So momentum of the football player, 110 times 8, 880. Momentum of the ball, 0.410 times 25, 10.3. So here's the momentum of the football player, here's the momentum of the ball. The momentum of the ball is about 1/10 or 1/8 the momentum of the player, right? 1/9 almost. I mean a little bit. Who's 1/9 actually? So momentum is the thing that is responsible in many cases for things being able to move one another. So if I'm pushing on you and you're pushing on me and we move each other in one way, maybe I slow down and you speed up, or whatever, or vice versa, or you turn, or whatever else. This transfer of movement from one thing to another is largely due to exchanging momentum back and forth. Okay, so some of my momentum goes into you as your momentum. It becomes your momentum essentially. So if a ball only has about 6 kilogram meters per second, has 10 kilogram meters per second of momentum, as opposed to the player at 880 kilogram meters per second, how realistic is it that a thrown football is going to make a player move? Like maybe you've seen a movie where somebody catches a ball and it actually knocks them over or something like this. It's not happening. The ball just doesn't carry that much momentum. You have to fire the ball out of a cannon for it to knock somebody over. And it's actually the same thing for bullets. Bullets carry very little momentum even though they have a very, very high speed. They have a lot of energy because remember that kinetic energy is 1/2 mv squared. So a bullet goes extremely fast and so has a lot of energy because it's v squared for the energy. Bullets have a ton of energy and that's why they can go through things. That's why they do damage, a lot of damage to people when they hit people or animals when they hit animals, right? However, they don't carry a lot of momentum. They'll do damage, they'll punch through the skin, they'll break bones, they'll tumble around and cause all kinds of internal damage. But they're not going to push anything over unless it's like a squirrel. Unless it's about, within 10 times the mass of the bullet. If it's within 10 times the mass of the bullet, it's just not going to do much. So again, movies that show people they get shot, they get knocked over or something, that's not realistic at all. Most of the time, when somebody gets shot, nobody even notices that they were shot, unless it was a really gruesome, like head wound or something. They just, I mean, a lot of times the person who gets shot doesn't even notice it because it doesn't push them around at all. It, from what I've heard, it's just like being bit. It's like just a really sharp, quick pain that is just shocking. I've actually been shot, but it didn't go into my skin. It was a ricochet. I shot myself. I had a ricochet off of a target that was a little too close. It came right back and hit me right in the stomach. So anyway, so it turns out that if you play around with the equation, momentum equals mass times velocity, right? If you play around with Newton's second law, you actually get this result. And they actually do it right here. Here is momentum. Momentum is mass times velocity. But if we change the momentum, if your momentum changes so that you're going slow and you go faster, or you're going fast and you go slower, or you're not going anywhere at all and you move and you start moving, whatever it is, if your momentum changes, that means you're going to have a change in your mass times your velocity. Well, of course, most people don't change their mass that quickly, right? It can be done, but it doesn't happen that often. Since the mass is considered to be a constant in many situations, we don't worry about the changing mass, we just worry about the changing velocity. Well, if this change in velocity happens over a time, if we divide it by an amount of time, and divide the momentum by an amount of time, because there's momentum on the left side of the equation, we get momentum divided by time equals mass times velocity divided by time, and change in velocity over change in time is acceleration. So this side of the equation is equal to mass times acceleration, which means that change in momentum over change in time equals force, because force equals mass times acceleration. So this gives us another equation right here. Net force equals a change in momentum over a change in time. If something's momentum changes in some amount of time, it will be due to a force. It's because a force acted on it, right? In other words, if something accelerates, it's because of a force. It's the same idea. Excuse me. But we use this equation to define something new, which we'll learn next section. So anyway, so new equation. So far we have essentially two equations that we've dealt with. Momentum equals mass times velocity. And remember, this is a vector equation. It cares about direction. So you can have a momentum going in the positive x direction. It would be a positive momentum. If you had the same speed and the same mass going in the exact opposite direction, it would be a negative momentum, whatever, a negative 10 kilogram meters per second. Momentum doesn't have its own unit. It's just called kilograms meters per second. And then we have this equation, which is actually right here. Net force equals change in momentum over change in time. Now remember, this can also equal mass times acceleration. So I like to write net force equals change in momentum over change in time equals mass times acceleration, because you can use all three of those together. So here we use this equation, this force equals change in momentum over change in time, to calculate how much force is applied to a tennis racket. Venus Williams hit the fastest recorded serve in women's tennis, speed of 58 meters per second. We want to know what's the force exerted on our 0.057 on the 0.057 kilogram tennis ball. Assuming that the ball's speed just after the impact is 58 meters per second, and the initial horizontal component of the velocity before impact is negligible or zero. And that the ball remained in contact with the racket for 5 milliseconds, or 0.005 seconds. So they've given us time, they've given us velocity after it's been hit, they've given us they've given us the mass right here. Right? So they've given us some good stuff. Here's our equation. Net force equals change in momentum over change in time. We're going to solve this because we want to know what is the change in, what do we want to know? But we want to know the force. So what we're going to do is we're going to try to solve this equation by solving for the change in momentum and then plugging in the change in time. The change in momentum is just mass times change in velocity. So velocity final minus velocity initial. And they tell us the final velocity is 58. The initial velocity is negligible or 0, so it's 58 minus 0. And we plug those things in for our mass and our velocity, the mass of the ball and the change in velocity of the ball. We get 3.306 kilogram meters per second for our change in momentum. That's great. So we know one thing. We know the change in momentum. Now we just need to figure out the change in time. Well, they've given us that too. It's 5 milliseconds, 5 times 10 minus 3 seconds. We take our answer to the change in momentum part and divide it by the answer to the change in time part. And then we go ahead and get an answer of 661 newtons. That's enough force, actually, to it's enough force to move a person, kind of a lightweight person, but a person, like a young person or a small person. 660 newtons. That's maybe, I guess that's close to about 100 pounds-ish. Oh man, tired. If we rearrange this equation, we get this equation, change in momentum, equals net force times change in time, and this is what we call impulse. The change in momentum in any situation is called the impulse. And this is one other reason. This is one other reason that boxers roll with the punches, right? Or the reason we have airbags. So impulse is change in momentum, and change in momentum, according to our equation, is equal to force times the change in time. So the change in momentum of a boxer's head is going to be the same whether or not they roll with the punch. If they get hit in the head and they don't roll with the punch, their head's going to go really quickly from 0 to whatever the top speed of the glove is. Right? So in other words, the time is going to be really small if they don't roll with the punch, because it's going to move very quickly. And that means the force has to be really big for this delta P to be what it needs to be. However, if you decide to roll with the punch so that that glove makes spends a lot more time hitting your face, the time that your head changes momentum goes up. You get a bigger change in time. And then what happens to the force? The force can be small, and you have a small force times a big time equals the change in momentum. So the kinds of acceleration that boxers feel is something like, I don't know, it's somewhere in the several meters per second kind of acceleration, which is pretty fast. Could be even in the tens of meters per second. They get moved pretty quickly over a fairly long distance for that amount of time. So this change in P here could be 5, for example. Let's say it's a 5. Let's say that the change in time, you allow this person to hit you, and it happens in about 0.01 seconds, right? So what do you have to multiply 0.01 by to get 5? Well, I'll tell you, it's 500. So you'd have a 500 Newton force times 0.01 seconds equals a change of 5 kilogram meters per second in momentum. So that's a very small time. What if we allow it to hit us for, that's a hundredth of a second, let's do a tenth of a second. What if we allow that hit to land for a tenth of a second by rolling our face so that the glove's in contact longer and our face moves with less acceleration? Well, now we only have to multiply by 50, so that's only 50 newtons. Let's see, how do I get out of this? I forgot. Okay, so that's impulse. Again, impulse is a vector equation. This cares about direction. So let's do a very simple example, right? They're not doing the one that I want to do. Let's do a simple example. Have any of you played pool before? Pool table? So you have your pool ball your cue lined up perfectly with the cue ball, and you hit it perfectly straight, and you hit another ball, right? So we're going to consider and you hit the other ball head on, perfectly straight on, so that the ball doesn't go off at any angle. So the one ball comes in, hits the other ball. We're going to consider our system to be the two balls. What happens? One ball's coming in straight, hits it head on the other ball. What happens to the first ball? We'll assume that the ball doesn't get any spin on it as well, because spin changes things. But what happens? The first ball stops, right? And then what does the second ball do? It takes off, right? The first ball hits the second ball, the first ball stops, and the second ball takes off with about the same speed as the first ball had, right? It's a little bit less because there's friction between the table and the balls, and the friction removes some of that momentum to the table, to the earth under the table and whatever else, kind of changes it with the earth, so it becomes unnoticeable. But it's still there. So that's a very simple example of this, of what happens with this transfer of momentum. However, what happens if you have two balls that are exactly the same, mass and size and everything, and they're rolling towards each other and they hit each other exactly straight on, and they have the same velocity just in the opposite direction? What's going to happen? Anybody guess? It's possible. It's possible. It really depends, it actually depends on if they bounce off of each other or not. If they're made of a really good bouncy material, that they're going to hit each other and bounce off and go in the opposite directions again with the same speeds, but in opposite directions. But if they're not very bouncy, let's say they're made of balls of putty or something, and then they stick together, and they just stick together and stop. And why is this? And this is because the momentum has direction, and it cares about that. So if the momentum is the same all the time in our system are these two balls rolling towards each other, then one of them has a momentum in one direction, the other one has a momentum in the exact opposite direction, but their momentums are essentially equal and opposite if they have the same mass and same velocity. So this one's momentum might be an arrow that long. This one's arrow would be an arrow of the same length, but in the opposite direction. So if you add momentum 1, actually they use P for momentum like everybody does. So momentum 1, P1, momentum 2, if these are the same mass, and mass, and they're going the same velocity, then P1 equals P2. Right? So that means that the total momentum, when you add them together, is P1 plus P2 equals 0, but actually P1 equals negative P2 because it cares about direction. P1, P2 has to equal 0 because they're negatives of each other. So this one plus the negative of itself will cancel each other out. They have a total momentum of 0 to start with. The total momentum is 0 because they cancel each other's momentums out. But after they're done colliding, the momentum still has to be 0. So these are two options. Either they stopped in the middle, or they bounced off each other and went in opposite directions, so that the first ball now has the negative momentum and the second ball has the positive momentum. And they still cancel out. Right? So let's calculate this one here. Let's do this example. we have two of these billiard balls or pool balls. They're going to hit now a wall. The first ball is going to come in and hit the wall straight on, dead on the wall. They don't have a picture of this, but we'll draw one in a second. So it goes straight into the wall and hits it and bounces straight back out. First ball. The second ball comes in to the wall at an angle, as if you're trying to bounce it off the wall, careen it off the wall at an angle and maybe hit a hard to reach something or a pocket or whatever. So it's going to come in at an angle of 30 degrees from the perpendicular, and it's going to bounce off at an angle of 30 degrees from the perpendicular. We want to know the direction of the force that the wall exerts on each ball and calculate the ratio of the magnitudes of the impulses on the two balls by the wall. So force first. How much does the wall push on the ball when the ball hits it? That's what we're going to figure out first. So here's our drawing. Here's our wall over here. We'll consider this direction the positive x direction. The first ball comes straight into the wall, hits the wall, bounces back out, like that, except right on top of its own path. Second one comes in here at 30 degrees to the perpendicular. You have to draw your perpendicular to get the picture right. So 30 degrees to the perpendicular, comes out 30 degrees to the perpendicular, like that. They want to know what is the ratio of this one, the force that the wall pushes this ball with compared to the force that this part of the wall pushes this ball with. Goodness, getting tired. Okay, so according to our equation, we have this equation that says force equals. Actually, the equation goes momentum, change in momentum, equals force divided by change in time. Okay, so change in momentum equals force divided by change in time. Did I do that right? No, I didn't do that right. Force times change in time. Make sure I got that right. Chain force times time. Yeah, chain momentum equals force times time. Chain of momentum equals force times time. Right there. That's the question. That's the correct one. And the change in momentum, we're trying to calculate the force, so we'll solve this for the force. Force equals change in momentum over change in time. So how do we calculate these? Well, the change in time, well, we'll have to get to that. Change in momentum, we'll have to figure that out too. The change in momentum, remember, is equal to mass times velocity. That means change in momentum equals mass times change in velocity. Well, they just told us their changes in velocity. That's in the problem, right? The problem is that this one has a velocity coming in and going out just in the x direction. So the x direction is this way. All the velocity for this one is in the x direction. But in this one, it has its velocity. If it's going 10 meters per second at an angle, then you have to break this into two components. There has to be one component that tells you its x velocity, so whatever that is. And one component tells you y velocity. Okay. Now, why do we care? Well, we care because if we can calculate the velocity of it coming into the wall when it bounces and comes out from the wall, this way, or this way, we should be able to calculate the final velocity, because this is the initial velocity of this ball is the ball coming in. The initial velocity of this is this ball coming in this way. Remember, this is a 30-degree angle, and this one right here is the length of the magnitude of the original velocity. So if we have this original velocity, then we want to know the x velocity this way, because that's the one that's perpendicular to our striking surface. So that's going to be this one here, which is going to be the sine of theta. So if this is velocity 1, and this is velocity 2, then this one's going to be velocity 2 sine theta, because it's next to the angle theta. Oops. Sine theta. That's theta. So that's V2 sine theta, right? And these are our initial velocities coming in. And then final velocities going out. Well, the final velocity of this one is going to be bounced over this direction. It's still going to have some downward movement. It's starting off with this downward velocity here. We don't care about that downward velocity because that's not the direction that this is going to be pushed by the wall with, right? The direction the wall pushes is this way. It pushes normal because it's a normal force. So the normal forces are the things that push the ball away from the wall. So they're going to be pointing perpendicular to the wall 90 degrees right here. And so all we care about is this part of the velocity in this direction, because we care about the change in momentum. Essentially what we're doing is we're going to have to do this in the x direction and in the y direction. But in the y direction, does the momentum change at all? Right here you have the x dimension. The x dimension, it starts by going towards the ball and it ends by going away from the wall. But in the y direction, you start by going down and you end by going still down, right? The y direction velocity of this thing doesn't change at all unless something is pushing in that direction. And we don't have anything that says it's pushing in that direction. So the change in velocity in the y direction, in other words, the change in momentum in the y direction, is actually 0 in this problem. Yep. So in the y direction, we don't have any force acting on the ball. And that makes sense because it's going the same speed to begin with in the y direction as it is in the end with. The only time it's changed its speed or direction is when it bounces off the ball and goes back the other direction. So this is kind of the picture we're looking at as we go forward with this problem. I might have to end class early today because I'm so exhausted. I'm having a hard time staying with it here. Okay, so now we get into this problem, and we see what they did. We have our first billiard ball it's just going straight towards the ball. Now they're using U instead of V, don't be too confused. But the momentum of the first ball initially is m mass times velocity, and they're saying the y momentum is 0 because it's not, the first ball is just going straight into the wall. It's not going perpendicular, it's not going parallel to the wall at all, right? Parallel to the wall is the y direction, straight into the wall is the x direction. So there is no parallel, there's no perpendicular component for the y side of things. The initial y momentum, the final y momentum in the first part is just 0. So, but why is there a negative sign here? Well, because it's changed direction. It's going into the wall, which is positive, a positive velocity. Out of the wall is a negative velocity. But the second ball is different. The second ball still has x components. That's the thing we calculated. We did it called a v cosine 30. They're doing a u cosine 30 here, u cosine 30. Where one of them is going into the wall, that's the positive one. And this one's coming out of the wall, that's the negative one. But again, the y version of it is the same. It's mu sine 30. Mu sine 30. It's still the same either way. So, So if we actually do the math here, we take the initial velocity, the initial momentum, sorry, the final momentum minus the initial momentum. Then we're taking this one and subtracting this one, so we get negative 2 times mu for the first half is the change in momentum. When we do the same thing here, we get negative mu minus mu, which is negative 2 times mu cosine 30. Right? Now what they want to know in this problem is they want to know the ratio between these changes. And it turns out that the ratio between these changes is actually 1 over the cosine 30, because the 2 times n times u just cancels out. So 1 over cosine 30 happens to be 2 over square root of 3. We write down there in the video. Now, like in the last chapter, where we had a force times distance, we had a force as a function of distance graph, and we took the area under the curve and got the energy. In a force time graph, we take the area under the curve and we're going to get the momentum. So that's useful. So what is conservation of momentum? It really just means that if you add up all the momentums when you start the problem, they have to equal all the momentums at the end of the problem. That's what it comes down to. So if you have a car and it bumps another car and makes the other car go faster and makes the first car go a little bit slower, then the faster car will gain some of the momentum of the slower car after the bump, right? Pretty straightforward. Also, you should remember that you can have multiple things with multiple momentums on either side, and you have to remember that it has a sign. The momentum can be positive or negative depending on which way it's moving, because velocities can be positive or negative depending on what's moving. Here's an interesting example where you have a rocket ship that's taking off, but it's all one piece to start with. And then somewhere near the top of its little ballistic curve here, it fires off this top nose cone. And what happens is the nose cone goes off into space. This is a very common way of launching a spacecraft. The nose cone is going to blast off from there and go into space. It's going to blast its rockets against the back of this thing. And what's going to happen to the back of this thing? If this rocket gets blasted off going this way, what happens to the bottom half of the rocket? It gets pushed down. Well, why? Well, think of it as momentum, conservation of momentum. We have this object that if we circle it and call this our system of interest, we're just looking at the rocket. Now we're pretending that the rocket is not necessarily moving through the sky, we're just looking at it. And it's sitting on a block of ice, so it's very low friction. And you shoot off one end of it, the back end will slide backwards slightly, right? And that's exactly what happens with rockets that are going into space. The top one fires another rocket, shoots off into space, and this bottom one just kind of floats back down the earth, or dives back down the earth. Now they've actually designed them so they can retro-fire and they can land again, but the momentum remains constant. This one continues to go up into space, this one goes down towards the ground, and eventually the total momentum will still be the same after they blow off of each other here. I'm tired. Gotta decide if I want to do any more. How many sections do we have? The next section is pretty involved. Yeah. The problem is that we kind of have to do at least the next two if we want to do our lab tomorrow. So we'll do the next two. So what it comes down to in the end is conservation of momentum in collisions. And collisions are our best way to make use of this stuff. So if we have two objects, two different masses, maybe they're cars on a track, or maybe they're blocks of ice on ice, or whatever, blocks of wood on ice, whatever they are. Doesn't matter what they are. If they come towards each other in a single line, so one-dimensionally, and they bounce off of each other perfectly. In other words, nothing from one object sticks to the other object, and the bounce has no loss of energy. If that happens, we call that an elastic collision, and it conserves two things. It conserves kinetic energy and potential energy. In other words, the kinetic energy at the beginning of the problem will equal the kinetic energy at the end, and the momentum will be conserved. The momentum at the beginning, a total of all the momentums added together, will equal all the momentums added together at the end. But remember, with energies, it's just numbers. With momentum, it is vectors, so it's numbers and directions. You've got to be aware of that. So here's our system. We have one block sliding forward and another one catching up to it. This one in the back is going faster. And it bumps the one in front, and it's a perfectly elastic collision. They bounce off of each other perfectly. There's no loss of energy. In the end, the second block is going faster than it was, and the first block bounced back, and now it's going in another direction, and it's going slower. It's smaller velocity. And they give us some numbers for those. Here are the equations that you need to solve for elastic collisions. There are two of them. The first one is the momentum equation. Sum of the momentums, the momentum of the first one plus the momentum of the second equals, at the beginning equals the momentum of the first plus the momentum of the second at the end. This is what it looks like if you break it down into masses times velocities, where this prime down here means that the final velocities. Right? But if you're doing a perfectly balanced elastic collision, you also have to solve the equation for the conservation of kinetic energies. 1/2 mv1 squared plus 1/2 m2v2 squared. All the kinetic energies at the beginning equal all the kinetic energies at the end. So here's an elastic collision. We have mass 1, mass 2, and we have the initial velocity of 1 and the initial velocity of 2. So the first one is moving, the second one is not to start. The smaller one, which is the 0.5 one, is moving. The second one, the bigger one, is not moving. The smaller one is going to hit the bigger one, and we want to see what happens. In every collision, momentum is conserved. So this equation is true. First momentum equals, the initial first momentum equals both the final momentums added together. Why is there not an initial momentum for block 2 in this one? The momentum is equal to the mass times the velocity. The velocity of block 2 at the beginning is 0. So it has no momentum according to our system, right? So momentum 2 is just 0, so they just don't write it down. So this is what the conservation of momentum equation is going to look like right here. Remember that velocities can turn out to be negative. That would mean that the velocity is going in the negative direction. If our positive direction is to the right, then our negative direction is to the left. Anything that comes out as a positive is going to be a right-hand going velocity. Anything that comes out negative would be a left-going velocity. Now, the second equation we need to solve is the conservation of kinetic energy equation. So there's kinetic energy in the first car to begin with, but none in the second car, so that was gone. There may be kinetic energy in the first and the second car. We know what's happening in the end because they told us, but maybe one of them could stop. That's entirely possible. So in this one, so what they're going to do here is they're going to try to solve these two equations to get what they're trying to get what the answer they're looking for. In this case, they want to know let's see, calculate the velocities of the two objects following an elastic collision. So we want to calculate velocity 1 and velocity 2 final, which means we're going to have to use both equations. So we're going to solve one of these equations for velocity 2. We solve the first one, the momentum equation, for velocity 2 final, and we get this equation. And then we plug this equation into this equation, this great big one, this crazy one. And they don't do it for you, but they plug this one into this one, volume 2. So they remove the volume 2, plug this thing in, and then they do all the math and create a formula for the velocity of the second block afterwards, and that gives you your answer. But how do they do that in practice? What's the real thing going on here? This is no different than when we were solving for two unknowns and two equations during our kinematic equations, except that in some of these cases, and often in these cases, you end up with a quadratic equation that you have to solve. You're going to have to test both answers logically and see if they make sense. So if you have one block that's stopped and another one comes and hits it, and then they're both going backwards when you're done because of your answers, then you didn't pick the right answers, right? So you have to logically work through the answers sometimes to figure out which one makes sense. And that's what they do there. So the last thing today, inelastic collisions. In a perfectly inelastic collision, kinetic energy is not conserved because the two objects will stick together and become one object. Okay? So you have these two come together and they stick together and they might still be moving, but in this case, they have equal masses and equal but opposite velocities, so they don't. It's like the example we talked about, two play balls rolling towards each other, have the same mass, the same velocity, but opposite directions for their velocities. Roll together, then they stick together and they just stop because they don't have any more momentum because their momentum's canceled. This momentum was negative of this momentum. So that adds to be a zero momentum. The total momentum was zero. When you add this positive momentum to this negative momentum, since they're equal and opposite, they add to be zero. Total momentum zero. Here the blocks aren't moving. Total momentum zero. Momentum conserved. That is always the case with momentum. As far as we can tell, there is no situation where momentum is not conserved. So let's see what happens to a goalie that's catching a puck. Because the goalie catches the puck in their glove, it's like the puck becomes part of the glove, which is part of the goalie, right? So before we start, the puck has some mass and velocity, and it's moving forward, and the goalie does not have any velocity, so all the momentum is in the puck. And afterwards, we're going to have a puck and a goalie, so we're going to add their masses together to make one object, and they're going to have one velocity moving backwards a little bit as the momentum of the puck to begin with becomes part of the momentum of the puck and the player combined. So this is what it looks like. You have your initial momentums for the puck and the player, and your final momentums for the puck and the player, but in our case, we don't need to treat them separately since they're going to have the same velocity to end up with. You can replace V1 prime and V2 prime with just V prime or V1 prime or whatever you want to call it, doesn't matter. They just replace it with V prime, the final velocity of both the player and the puck. And then you add the masses together to show that they're all one mass. And then this equation becomes very simple to solve actually. If you know the masses of each thing and you know the initial velocity of the first thing, you can calculate the final velocity of the puck plus player. And they do. Then in part B, they show us that the kinetic energies are not conserved. The initial kinetic energy of the puck is 91 joules. And then the final kinetic energy of the puck and the player turns out to be 0.196 joules. That's not conserved energy. We lost almost all of the energy, right? When you catch it, and that is lost as the puck makes a sound, as the puck warms up the glove because there will be some friction there, and then as the puck deforms the glove, it will deform the glove and cause it to close around the puck usually, or bend or squish or something. But energy can also be lost in pain in the player's hand, right? Things like that. Heat that's lost as the arm moves or whatever else. So lots of things can happen. Now, I'm going to leave the last example for you guys to do on your own in the lab tomorrow, because you'll be doing a lot of that in the lab tomorrow. On Thursday, on Wednesday rather, we'll finish up chapter 8, answer any questions you have for chapter 8. So highly recommend today and tomorrow you get started on chapter 8, so we don't have this this situation going where we are asking questions over the weekend. We really want to avoid asking questions on homework over the weekend because I'm not available as much over the weekend. We don't communicate as much over the weekend. So what we want to do is have this homework mostly done by Wednesday, so that we can answer any questions that you have and you can finish it up by Wednesday. We'd really like to get on a track like that if we can do it. That would be great. So finish up homework 7 today. Get started on homework 8 tonight or tomorrow, so that you've got most of it done and you can ask any questions you have on Wednesday. We'll finish up chapter 8, answer any questions on chapter 8, and then hopefully we'll even have some time to get started on chapter 9. So we're moving right along. And we'll end a little early today so that I don't fall asleep and embarrass myself by hitting my head on the keyboard or something. Anybody have any questions or concerns or problems or anything? Okay. Name that. I am done. You are welcome to skedaddle at your earliest convenience.